So last time we said that we'll have a lesson on vector operations, and what I was trying to convey is that we are going to primarily say that uh, these vector operations are going to help us in doing calculations. So I had said one, they'll make the formula of physics uh, more compact and also help us in performing calculations in a very efficient manner. So I just want to tell you that uh, this is our immediate concern, but if you look beyond this, one can ask a deep question as to why the formulae of physics are we are being able to represent the formulae of physics with these vector notation. And one can ask a question, why is this? Because it's going to happen repeatedly that we are able to express the formula in terms of vectors. And there is a nice answer to this question, which is definitely a difficult one. And I would suggest you read lecture 8 of volume 1 Feynman Physics. Okay, so this can be a good reading, and you may have to reread before you actually get on to it, but that's fine. But let's instead focus on our immediate concern, that is these two aspects. So the first is vector dot product. Vector dot product. Now we already know what is work. So suppose there's an object that displaces, then this is a vector. So it displaces from point A to point B, and this is the displacement vector. Suppose it got displaced due to the action of a force along this line, which was in this direction. Then this product we saw in the WorkEnergy Theorem, F cos theta into S, which is the magnitude of the displacement vector. This product, magnitude of the force into cos of theta into magnitude of S into cos theta, is what we call as the work done by this force in this displacement. Okay, so now this involves a vector F, a vector, another vector displacement. So these two vectors together give us a scalar quantity called work, which is defined in this manner, and we know that this is useful in a very important formula in physics, that is the work energy theorem. So this is what we define as the scalar dot product. Oh, see, I made a mistake here. Okay, so scalar dot product of two vectors. That's what I really wanted to write. Right. So two vectors combined together to give a scalar quantity. You can see that there is no arrow over W, and these are the two vectors, displacement and force, and the magnitude of the force multiplied by the magnitude of the displacement into cos of the angle between them. Now this is called the dot product of two vectors, right? So let's write it formally. A vector A and a vector B, and the angle between them happens to be theta. Then the dot product here, the dot signifies that it's a scalar dot product, and we define this operation between two vectors to be equal to mod of A mod of B into cos of theta. And we study this as a mathematical operation between two vectors. So we know what vectors are. So we take one vector, you take another vector, and then you combine them. That means you operate them, you create an operation between the two vectors, and then you say that you define it to be a scalar quantity. For example, this is a scalar quantity, this is a scalar quantity, this is a scalar quantity. Multiply all of them together, and this is the so-called scalar dot product, and you are already convinced that this product is useful. So for example, now you know that if you have a path from A to B, and we have done this in the WorkEnergy theorem, and you break up the path. I'm just breaking it up into some finite number of pieces, and you know that you can just make smaller and smaller pieces of this and add up all the work. Shall I just call it dw1, dw2, dw3, dw4 and dw5. Add up all the work done on all these parts, make smaller and smaller parts, add them, and then you can tell that the total work done, which is the summation of all the work I ranging from 1 to infinity by making it up into really small parts, is equal to the final kinetic energy minus the initial kinetic energy. Now this theorem of the WorkEnergy theorem of physics is written as this summation is called integral of the work done, which is the force dot product with the displacement. So this can be considered as the first displacement, this can be considered as the second displacement, this can be considered as the third displacement, and all the displacements you do this dot product between the forces. So for example, while it is displacing, maybe the force was in this direction, and then this was the angle theta 1, and so on. So you add up the dot product, and so you are very clear about the fact that f is a vector, displacement is a vector, and you're adding up by breaking up into small pieces, and this is equal to the delta ke, and you can see how neatly the whole theorem is presented in a very accurate fashion with the help of a vector operation, an operation on vectors, which is the scalar dot product. Okay, now I just want to quickly remind you that, look, we have studied operations on vectors, okay, before, and we've already seen how useful it is. For example, we've studied what do you mean by A plus B or A minus B, and this itself was so useful till now, okay, because the main law for us has been this one, which is clearly a vector equation, and we've been in positions where we have to add up the vectors, and therefore, you know, so therefore we've often felt the need to do this operation. Now whilst doing this, we have realized that this operation, a property of this operation, was crucial. In fact, two actually. A plus B is equal to B plus A, and I just want to remind you that we saw a silly graphical proof of this, The other property which sometimes gets forgotten is that the brackets are not important. So when you want to add a lot of vectors, okay, the brackets are not important. And to say it more nicely, you can put brackets wherever you feel like. And what this really means is that this addition is associative, and we made full use of these two properties to do this process very efficiently. And that's really what I mean by saying that is helping us to do calculations. Actually, we've already met this calculation aspect of vectors. Now, the other aspect is, oh my god, how come the law is stated so compactly with vectors? I said Feynman will give you an answer. And yeah, right? So, and it's compact. Okay, so all the three things are visible on this page. Now, I want to tell you that these two properties are important, and therefore the next question to ask is, does the dot product have any properties? Obviously these properties are not to be flouted, number one, and number two is that it might help us to do the calculations very well, very cleverly. So one gets slowly to realize that the properties are the ones that will help us to do the calculations well. Well, here too there are two important properties, okay, and one is A dot B, and it's good to write all the three things is equal to B dot A. This is called commutative property of the dot product. And now there's another property that is going to be extremely crucial in the way we do our calculations, and that is A dot B plus C, which we already know is a vector. So for example, we know that B plus C gives another vector, and obviously another vector can be dotted with another vector, but this happens to be equal to A dot B plus A dot C. I just want to quickly tell you that a good question to ask is, can we convince ourselves that this is true? And once we are convinced that this is true, then how does it help in how does this help in the calculation? So these are the two aspects I'll touch upon in the next video. But right now, why don't you try and see whether these things are proved in your favorite textbooks. In any case, I'm going to talk about it, but it might be good for you to see whether your textbook mentions that these two statements need a proof, and then of course how to exploit it for the calculations is also a very simple aspect. We'll get to it in a minute, but let me just stop this video right now.